So let's imagine that we have a mass on a spring. We're going to have it on a table here. We're going to slide it. We're going to start this at our, what we call x equals 0. Refer to this again as an equilibrium state. All forces are in balance at this point. Alright, what I'm going to do next then is, well, let's just conceptualize this. So I'm going to push with the force this way. It's going to start to compress the spring. Push it some distance, we'll just say d. So again, the concept is I'm applying a force over a distance. I'm doing work onto it, and that energy is now stored within the spring. Now some elastic things like the rubber band, it only works when you stretch it, right? When you pull on it, then it's stored. It doesn't work when you push on it. You don't store the energy in it that way. However, with springs, or ideal springs, which is what we're going to be working with mainly, it works both if I pull it down and let it go, or the opposite. So if I compress the spring and let it go, I can also store energy in that way. So that's what I'm doing here. In this case, I'm compressing it, but it would also work if I pull it this way, right? If I pull it this way, some distance, x equals d, I can also store energy in it in this case. Yeah?
Does it equal work done when you let it go?
It does equal work done, yeah.
So if you move it the same distance that way or that way?
It would be the same, yeah. So if I move it, 10 centimeters this way or 10 centimeters this way, it would be the same amount of work done into it. Alright, so let's look at what this is going to be. So the energy stored, so this is called spring potential energy. So it's a new type of potential energy. And again, this would simply be energy stored in a spring. Spring. There we go. Symbol we use is going to be U. U just means potential energy. So we'll just subscript this S. And the equation for this looks like this: 1/2 k x squared. 1/2 kx squared. So what are these? What's x, first of all? Okay, so it can either be like compressed or stretched. And what do you think K is? Yeah, so K has to deal with the spring itself, right? If it was just simply 1/2 x squared, then every spring would store the same amount of energy. But every spring, all springs are different, right? So K is what we call either the spring constant or the force constant. Okay, and it's just a function of the spring itself. The units, let's look at the units because this will really help you understand the concept of the spring constant. So units are newtons per meter. Newtons per meter. So for example, let's just look at 2. So if you have 5 newtons per meter or 20 newtons per meter, so what 5 newtons per meter means is to stretch your spring by 1 meter, you need 5 newtons of force. So if you give your spring 5 newtons of force, it will stretch it by 1 meter. To stretch this one by 1 meter, you need 20 newtons of force. Okay? So in which of these two would be a stiffer spring? The 20, right? So you need more force to stretch it 1 meter, right? You need to use 4 times as much force to stretch it 1 meter. So that's kind of the meaning of this. And again, it's just the stiffness of the springs. All springs are going to have different values for the spring constant. Okay? Any questions on this idea, concept? So let's go do an example.